So as I mentioned, this presentation was inspired because I do have some customers doing in-vehicle measurement. However, as you all know, corporate people don't often like to share their data with guys like me to share to the world. So a friend of mine has a electric scooter, and he was kind enough to let me do some measurements on it because he's also a nerd. So I took one of these electric scooters. I found the three phase voltages, so I pulled out the phase wires. I threw a Genesis system over the handlebars. I connected those voltage, took the voltage measurement. I took the current measurements. I hooked it up to a battery, and I had a laptop going for review. So it was quite the system on the scooter, but it did a really nice job of demonstrating mobile testing, and the unit being 12 volts, having the ability to stream it to a laptop made this actually a really simple process. And what did I find? Well, one thing that several customers have done now is they'll run their vehicle at different grades of hills to get different information. So went out to a track, which was just a local park, and found a little course with some hills. And here's the data I had. So on the top, in the red, I have the instantaneous voltage, and in the blue, I have my RMS voltage, and we can see that the voltage moves around a little bit, but stays fairly stiff. I have my instantaneous current, my RMS current. We can see when we're loading and unloading the machine. And then what I think is the most interesting and probably tells us the most about the test is, again, I have my power in black, my reactive power in purple, and then my apparent power in orange. And if we go through this test, we can see that there's times where I had full acceleration, where I was coasting, where I was braking and going into regeneration, full power trying to get a characterization. We can see that this machine actually limits its power to 700 watts. Here's an acceleration downhill where we're using constantly less power. And there's some interesting stuff that comes from this, like when we enter regeneration. I mean, maybe you want to understand how a competitor enters regeneration, what a competitor's max power output is, how they handle hills, how they handle braking. So I think there's a lot of insight that can be found. And this little dip right here, this is if you kick the scooter, its control turns off temporarily. And all this gave me a really powerful reverse engineering tool. I could see that it was a 3-phase, 24-pole machine, 38-volt DC bus. And you can really start to understand this. And if I were to go find 3 different brand scooters, we can see if they had different control techniques, how they handled transients differently. So interesting stuff. Now, if we dig into some of these scenarios closer, I think we hit home some interesting facts and also some of the strengths of the eDrive system. In the top graph here, I've got my 3-phase currents in red, my cycle detect in black, my 3-phase voltages in blue, and then my powers at the bottom again. And we can see that in the scooter, you have to kick the scooter to get it started. So you actually have to kick it, and you see in the blue the back EMF. So it's a permanent magnet machine. Then the inverter kicks on, and we start to get current applied. Actually, initially, the scooter is regenerating power, so it's putting power back into the battery because we had kicked it. That cycle detect works really well, even through that little period where there's almost no current. And then it's driving the motor. It starts applying power, starts using real power. And as that frequency is ramping up, this is a real world scenario. So we're getting wind hitting us. We're getting all kinds of fun scenarios. And you can see that power kind of walk, but you can see your acceleration times. You can see that when we get to this peak point, we actually overshoot on power a little bit. We get these additional losses because the controller is trying to rein itself in as we speed up. So some really interesting stuff, but it's a very nice example of how you can dynamically measure that power during things like a startup. Let's see. Here's some example of some real world dynamics. So we're cruising at full throttle. We go into a coast mode, and you can see in that coast we go into regeneration. And how we enter that regeneration is important because if handled poorly, this could result in a poor user experience where you're switching in and out of regeneration really quickly and you end up feeling that. Or sometimes by going into regeneration, if you don't have enough power available, you end up burning more than you put back into the battery. So it makes an inefficient system, which is an interesting thing to think of. how we handle acceleration rates, and when you start comparing things like acceleration rates to accelerometers to video, you can see how the user reacts to that. Also, in the real world, drivers are sporadic. And if you want to know, what the efficiency set is for city driving, where it's start, stop, or start, slam on the accelerator, stop, or how a guy with a lead foot handles wear and tear on a vehicle, in-vehicle power measurements are a really nice thing. I know one example we have is looking at how a user abuses a gearbox. So if you're slamming on the accelerator and the brake, accelerator brake, and you start jamming up this gearbox, it can have degradation effects. So knowing maybe how to limit acceleration rates to improve the lifetime of the mechanical system down the line could be very useful. And then this downhill acceleration is an interesting step here, because you end up with these kind of power sways, and this is actually me kind of carving back and forth on the scooter and some hills and bumps and stuff. So taking into account how you handle things like that is also interesting. Slowing down, and this is mostly a conversation about regeneration. So if you look at the currents, we have this full current. Our powers start to wane off, and this is us slowing down. And then the system decides, okay, I'm safe to go into regeneration. We go into regeneration. We're there for a while. And then while we're still slowing down at some point, that power goes back into real power, and it goes back into losses. So we're no longer putting this power into the battery, and yet we're slowing down. And our currents are waning off, and our PWM is getting kind of funky out towards the end here. So I think this is an interesting example of, this designer might have poorly handled this. Maybe this could have been done better. Maybe we could have not eaten these losses at the sake of slowing down. And then we get some insight into how our PWM and our currents react under light load or no load situations. Are there losses here that are not being accounted for? So again, these interesting scenarios of how does my system, when coupled with all the other subsystems, react? How do these things affect the user experience? Can we feel this result of that electric powertrain coming into the vehicle, maybe that steering wheel, that pedal experience? And then maybe most importantly, how do our competitors do it? If you're bidding on a project, you might want to know how competitor A handles this so you can improve that problem. I think it's kind of straightforward stuff, but this is a real tool to understand what the electric machine's influence on that is. My favorite slide of the presentation. So naturally, being the engineer I am, I had to take this a step too far. So I had to jump on my scooter. So we were steady state cruising along. We jump, and the jump is an interesting thing, and it really applies to the motorcycle, the e-bike people of the world. But there are scenarios where a vehicle is going to get a wheel off the ground, and that frequency speeds way up because that machine's trying to hold torque, it's trying to hold power, and immediately you remove that load, and it speeds way up, and the amplitude of the current goes way down. We can see the PWM speeds way up. And actually, just due to the inertia of the wheel, we get a little bit of regeneration and the power kind of all over the place. But the landing is the important part. And the landing, we see this big inrush of current. And this inrush is, it's about a 50 amp peak on a steady state 30 amp system. So that's a pretty significant overshoot when we start thinking about what the rating of our wire is, and can this wire handle this, and how long is it going on for? And then we see that transient power again, and then it steadies off once the machine's recovered. But understanding these scenarios of what happens when I swerve, what happens if I'm on a motorcycle and I land, how do I handle a road in Detroit that's filled with potholes? I live on a road with a lot of potholes in Detroit. Could be scenarios that you want to look at from the powertrain perspective. So dynamic efficiency on a test stand. So we've gone out, we've taken all this really good data out in the field, and we're having a failure in a gearbox, and we want to understand that better. Well, you could take that profile back to your dyno, replay it, and just run kind of your golden degradation set on that machine. Or another alternative for that, and this is a thing we have several customers doing, is drive cycle testing. So the EPA and other governing bodies have 30-minute drive cycles where they give a speed profile and a torque profile for a given period of time. and they run through those, and they're looking for total energy used. So they're looking for the motor losses over that time. They're looking at temperatures over that time. But really, they want to optimize the system point by point. If you just look at total energy flow, you might get some information, but you're not isolating your losses. So by taking things like a golden set or taking things like a drive cycle, you can understand where your machine operates poorly and why it operates poorly, and take measures to improve those, take measures to mitigate losses. So you can correlate that dyno work to that lab work and really start to optimize and do some cool things with the test. Correlation over CAN. This slide's really just to hit home that we offer the output onto a CAN bus from all those real-time equations. So in the top, we have that PWM data. We're storing that data at 2 megasamples per second. We're storing that locally on the eDrive unit. And then we're also publishing those results onto a CAN bus for correlation. So we can take our RMS current and our RMS voltage and read those into something like an EDAC, read our powers into an EDAC, and process those and store them, at 100 hertz versus a megahertz, and have all that data synchronized in one place. So really nice ability. You end up with 2 data sets, one at the high-speed data, one at the correlated data. But in all likelihood, there's going to be different groups looking at these things. So it is a very nice way to kill 2 birds with 1 stone in a vehicle test. Dynamic controls work. I think this is really interesting. So because the eDrive system has the ability to program your own equations, you can start to do things like look at the machine in the control domain. Now on my scooter, I did not have position because I didn't have access to their resolver, but if you did, you could potentially get position from it. And then you can start, while in the vehicle, this is an example of a startup, the alpha beta phase. We start at 0 current, the machine starts to start up, and we can watch the current kind of unfold itself and how it operates in the control domain. And we can start to look at that, maybe space vector PWM control circle. Or if we have angle, we can look at the DQ0. View these in scope traces as in real time. This gives us more ability to do reverse engineering. We can see that point that's sitting out here and how it fluctuates if we change loading, how it fluctuates while we do a startup, a hard startup, a soft startup. This is going to come into play with those guys who are doing calibration and really, again, getting back to that experiential. How does this perform in the vehicle? Does this BMW perform like a BMW? Does this Corvette perform like a Corvette? Especially when we start electrifying, this definition of car experience is becoming a cool topic. And again, I wouldn't be doing my controls work justice if I didn't talk about my scooter jump. These extreme conditions and how we handle these transient scenarios can be really important. And maybe you have a maximum current that your machine can't go outside of, because if I have too much ID, I'm going to demagnetize my magnets. Well, you could put a little circle up on the screen and say, okay, this is my worst case circle. If I go outside of this, it's game over for my machine. I need to reevaluate my control technique. And you can follow that current as that scooter lands and see that it stays within the circle. Now, I drew an arbitrary circle because I don't know what's acceptable for these guys, but I think it opens up a really cool ability to understand how not only your machine works, but possibly how competitive machines work. So